This video is on geometric sequences. A geometric sequence has a common ratio between terms. Each term is multiplied by a factor to get to the next term. So here's some examples. This here is a geometric sequence because there is a common ratio between terms, and the common ratio is times 2. Each term is multiplied by 2 to get to the next term in the sequence. So 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16, like this. So each term is multiplied by 2 to get to the next term in the sequence. This here is a geometric sequence because there is a common ratio between each term of times a half. 1 times a half is a half times a half is a quarter times a half is 1/8. And this here is a geometric sequence because it has a common ratio between terms of times minus 2. 3 times minus 2 is minus 6, minus 6 times minus 2 is positive 12, positive 12 times minus 2 is minus 24. This is something called an alternating sequence here. An alternating sequence is when we alternate between positive and negative numbers. So this here is positive, this is negative, then it's positive, and this is negative. This is an alternating sequence. This is always the case when the common ratio is a negative number, because that's just what happens when you multiply by negative numbers. So for any geometric sequence, we can find un, or the nth term. So un, which is also the nth term. We talked about what un is in the previous video, arithmetic sequences. Really quick, just a recap. Un is what term we're talking about. So for the first sequence, let's say that we wanted to find u3. This would be the third term in the sequence. So it would be 1, 2, 3. So it would be this term here. So u3 would be equal to 8. And we use the same symbol un for all sequences, arithmetic or geometric. So for any geometric sequence, un is equal to ar to the power of n minus 1, where a is equal to the first term. So for the first sequence here, this a would be 2. R is the common ratio, and this is the thing we've already talked about what is multiplied each time. So R for this first sequence would be 2. And then n is the nth term. It's what term we're talking about. We're talking about the first term, the second term, or the third term, etc. So for example, for this first sequence, if we wanted to find u5, this would be the fifth term, and we can use this formula, sub in a, r, and n in order to find the fifth term. So a would be 2. And remember, there is a multiplication symbol here. So it's going to be times r, which you also said was 2, to the power of n minus 1. We're talking about the fifth term in the sequence. So therefore, n is going to be equal to 5. So it's going to be to the power of 5 minus 1. So this is going to be equal to, if we put this into a calculator, it's going to be equal to 32. So the fifth term in this sequence is 32. And you can see this if you just expand the sequence. 16 times 2 is equal to 32. So the fifth term in the sequence is 32. For this sequence, if we wanted to find u7, the seventh sequence, the seventh term, it would be a, which is 1, times r, which is half. Now, whenever we do a fraction as r, we always put it in a bracket because we want the whole fraction to be put to the power of n minus 1 here, and we need to put the bracket in order to do this. To the power of n minus 1, it's u7, so it's going to be to the power of 7 minus 1. And if you put this into a calculator, this is equal to 1 over 64. For this sequence here, if we wanted to find u10, the 10th term in the sequence, it would be, so a is equal to 3 times then r is equal to minus 2. The same thing as before, we have to put the minus 2 in the bracket because we want the minus to be included in the r. We want to put the whole r to the power of n minus 1. And then n is equal to 10, so it's going to be to the power of 10 minus 1. And if you put this into your calculator, you get the value of minus 1536, like this. Now, one really quick thing I just want to touch on. Let's say they gave an example, a sequence, where the first term is 2. They didn't give us the second term, but they told us that the third term is 8, and it's just a normal sequence. It goes on and on and on. And we want to find r, the common ratio. So the way that we can do this is just by using this third term here and just considering this and putting this into the formula. So u3 would be equal to, so a is equal to 2 times, and then r we don't know, so we'll just leave this as r, to the power of n minus 1. It's the third term, so it's going to be to the power of 3 minus 1, and this is going to be 2r to the power of 2. And this is equal to the third term, which is 8. And we can rearrange in order to find r. Divide both sides by 2 to get r squared is equal to 4. So therefore r is going to be equal to the square root of 4, which is going to be equal to 2. So r is equal to 2, and this makes sense. 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16. This is actually the sequence that we talked about right at the start of the first sequence. However, this isn't the only answer, because this square root here could be positive or negative, and such r could be positive or negative too. So r could be minus 2, and this would create an alternating sequence, which we talked about before. It would be 2, and then 2 times minus 2 is minus 4, minus 4 times minus 2 is 8, and then 8 times minus 2 is minus 16, and then so on and so forth. The first term is still 2, and the third term is still 8, but we've got two different sequences, because this could be minus 4 and this is 4 like this. So it could be an alternating sequence like this. So just be aware that this could be the case, especially if they do something like this with the first and the third term given. It could be an alternating sequence. Now, a lot of the time questions will say something like, given all the terms are positive, and therefore from this you can confirm that it's not going to be this sequence, as we've got negative terms here, and therefore it will have to be this sequence here. So it could say that, and you can be aware of that, therefore it will only be one of these sequences. But be aware of the idea that r could be positive or negative in these cases. And as well, you won't always need to consider this, because if they did something where the first term is 2 and the second term is 4, the way alternating sequences work, there is no way r could be minus 2 here, because it has to be either it has to be minus 4 to be the alternating sequence. So it has to be this sequence here. So you don't always need to consider it. So here's an example question about geometric sequences. So for part A, we need to find the 8th term in the sequence, and we can do this by using the formula un is equal to ar to the power of n minus 1 like this, and we can find the values of a, r, and n. So a is equal to 5, as that's the first term. R is the common ratio. You can see that each time it goes up by times 2. 5 times 2 is 10, 10 times 2 is 20, 20 times 2 is 40. So the common ratio is 2, and then n is going to be, because we want to find the 8th term, it's going to be 8. So therefore u8, as we find in the 8th term, is equal to 5 times 2 to the power of 8 minus 1. And if you put that into a calculator, that's equal to 640. So the 8th term, sorry, is 640. And then for part B, we need to find the value of n such that un is equal to 5120. So this is still going to be the same values of a is equal to 5 and r is equal to 2. And we need to find the value of n, and what we need to do is, using the formula un is equal to ar to the power of n minus 1, sub 5120 as un, sub in a and r as 5 and 2 respectively, and then we can rearrange in order to find the value of n. So it's going to be 5120 is equal to a, which is 5, times r, which is 2 to the power of n minus 1. Divide both sides by 5 to get 1024 is equal to 2 to the power of n minus 1 like this. And this is, now we have to do logs. We went over logs in a previous video. Go back to the kind of logs video if you need a refresher of how to do this. But what we need to do in order to get this exponential here is log both sides of the base 2. So this is going to be log base 2 of 1024, and this is going to be equal to, if we do log base 2 of this side, we're just going to be left with n minus 1 like this. Log base 2 of 1024, if you put it into a calculator, is equal to 10, and this is equal to n minus 1, so therefore n is just equal to 11. So therefore n is equal to 11, u11 is equal to 5120, and that's the final answer. We discussed this in the last video. A series is a sequence, but the terms are added together. So these are two of the exact same geometric progressions at the start, but they are now series instead of sequences because the terms are added together like this. This here is the alternating sequence. It can look quite confusing with these pluses and minuses like this, but this is a geometric series. So we can find Sn for any geometric series. We discussed this in the previous video, what Sn means. It's the first n terms of the series added together, where n is this number here. So, for example, if we were to find S4 for this series here, it would be the first four terms added together. So it would be 2 plus 4 plus 8 plus 16, as these are the first four terms. You put this into a calculator, this is equal to 30. So S4, the first four terms added together, is 30. But as we said, we can find Sn for any geometric series and for any value of n. Sn is equal to a and then 1 minus r to the power of n, and this is over 1 minus r here. Again, like before, where a is the first term, r is the common ratio, and n is the term that we're going up to. This is given in the formula booklet, and in the book it gives another formula as well. This formula is a and then r to the power of n minus 1, and this is over r minus 1, like this. This is of course the same thing because we've just multiplied the numerator and the denominator by minus 1. The book says that this version is better if r is bigger than 1, as the denominator will therefore be positive, but I don't think it really makes too much difference, and it isn't given to you in the formula booklet, so I would just focus on this one here. So for example, let's say that we wanted to find S9 for this first series here. S9 would be equal to, so A is the first term and it's 2, so it's going to be 2, and then it's going to be 1 minus R, and as we talked about before, R is 2 because we multiply each term by 2 to get to the next one. 2 times 2 is 4, 4 times 2 is 8, so it's going to be 2, and then to the power of n, and then n is going to be 9, we're adding the first 9 terms together, and this is going to be over 1 minus R, so it's going to be 1 minus 2. And if you put this into a calculator, it gives out the value of 1022. If we wanted to find S11 for this series here, so it would be S11, and this is equal to, so A is the first term and it's 3, and then it's going to be 1 minus r, and r, as we talked about before, is minus 2 because you times by minus 2 to get from one term to the other. So it's going to be minus 2, and we put this minus 2 in this bracket here, so the whole thing is put to the power of n, and n is 11, like this, and this is over 1 minus r, so it's going to be 1 minus 2, like this. And if you put this into a calculator, this is equal to 2049. The first 11 terms of this series added together is 2049. So here's an example question about geometric series. I've given you the formula for Sn for a geometric series. It's given to you in the formula book, so you'll have it in the exam. So for part A, we need to find S3, and we can just use this formula here. And this is really easy because it tells us what the first term and the common ratio is. A is the first term, 2 over 3, and R is the common ratio, 3, and N is going to be 3, as we need to find S3. So therefore, S3 is equal to 2 over 3 of 1 minus 3 to the power of 3 over 1 minus 3. We've just subbed in the values of R, N, and A into this, and if you put this into your calculator, this is equal to 26 over 3. S3 is equal to 26 over 3. And then for part B, we need to find the value of n such that Sn is equal to 6560 over 3. So what we just need to do is use this formula here, sub in the values of A and R, and then equal this to 6560 over 3, and rearrange in order to find the value of n. So Sn is going to be 6560 over 3. And this is equal to, so A, which is 2 over 3, 1 minus r, which is 3, and then to the power of n, we don't know what n is, we're rearranging to find it, over 1 minus r, which is 3. So this is going to be 6560 over 3 is equal to 2 over 3 of 1 minus 3 to the power of n over minus 2, and then times both sides by minus 2, and if you put it into a calculator, it's minus 13120 over 3 is equal to 2 over 3, 1 minus 3 to the power of n. I'm going to divide both sides by 2 over 3 because this whole thing is being times by 2 over 3 here. So if we divide both sides by 2 over 3, it will get rid of this here. And if you do this and put it into a calculator, it's going to be minus 6560 is equal to 1 minus 3 to the power of n. Move the 1 onto the other side to get minus 6561 is equal to minus 3 to the power of n. And then times both sides by minus 1, just get rid of the minus to do 6561 is equal to 3 to the power of n like this, and this is again where you need logs. Again, go back to the log video if you're not sure about this, but we need to find this value of n here, so we need to do log base 3 of both sides, so log base 3 of 6561 is equal to n, and if you put this into your calculator, n is equal to 8. So therefore S8 is equal to 6560 over 3. Like for an arithmetic series, the spec specifically says that you could be asked to prove the formula for Sn for a geometric series. There's a specific way to do it, and I would learn how to do it. I mean, it's slightly different to arithmetic series as well, so I would know how to do it. So we need to prove that the sum of the first n terms, so Sn, for a geometric series is this. So first of all, let's start off by writing Sn. So Sn is going to be equal to, and then what it is, it's the series of all the terms added together. So the first term is a, and then the second term is ar, the third term is ar squared, the fourth term is ar to the power of 3, and this is going to go on and on and on, and we'll do the final two terms here until ar to the power of n minus 2 plus ar to the power of n minus 1. So this is Sn here. If you want to confirm that these are the terms and understand it, un is equal to ar to the power of n minus 1. Sub in some values for n if you're a bit unsure. You can see that if you the nth term, if you sub in n, is going to be this ar to the power of n minus 1. This is going to be the n minus 1th term, stuff like that. This is the first term if you sub in n as 1, stuff like that. So do a bit of that if you're a bit confused about where we've got these from. So what we're going to do now is we're going to write out Sn again. But what we're going to do is we're going to times Sn by r, the common ratio. And what this is going to do is, so this here, all the terms are going to be times by r. So this a is now going to become ar, this ar is now going to become ar squared, stuff like that. And we're going to write this out, but we're going to write this out with kind of doing the pairs underneath them and basically shifting everything to the right by 1. So timesing everything by r, this a will become ar, I'm going to write it here, and then it's going to be ar squared plus ar cubed, and this is going to go on and on and on. Ar to the power of n minus 2 plus ar to the power of n minus 1. But you notice there's no term here, and that is because, as I said, everything's been shifted to the right by 1 with the way that we're writing it, to the point where we're going to have a final term here, and it's going to be when this here is multiplied by r, and this is going to become now ar to the power of n, because the minus 1 is going to go away when we times by r, because of the way the indices rule works. So now we've got this, and now what we're going to do is we're going to do Sn minus Rsn like this. And you can see that every single value is going to cancel out except for 2, the two that don't have a pair. A doesn't have a pair, and ar to the power of n doesn't have a pair, so these are still going to be present. So Sn minus Rsn is going to be equal to, so this is still going to be here a, and because we're minusing Rsn, this is now going to be minus, it's going to be minus ar to the power of n. So everything else is cancelled out except for that. What we're going to do is we're going to factor out the a, so it's going to be a of 1 minus r to the power of n, and then we're going to actually factor out the Sn from this. So we're going to do Sn, so this here is now just going to be 1 minus, and this here is just going to be r, and this is equal to a1 minus r to the power of n like that. And then we're going to divide both sides by 1 minus r, so it cancels out on this side, so it's going to become Sn is equal to a1 minus r to the power of n over 1 minus r. So that is the proof. So again, you need to know how to prove Sn for geometric and arithmetic series. The spec specifically says that you do. Here we have two different geometric series. We have this one up here, 1 plus 2 plus 4 plus 8, and we can see that it has a common ratio to go from term to term of times 2, like this. So r is equal to 2. Here we have another geometric series, and we can see that to go from one term to another like this, we times by a half. So r is equal to a half. And the key to this is up here, r is bigger than 1. And down here, r is less than 1. So this geometric series up here, this is known as divergent. So what divergent means is as n approaches infinity, so as we increase the amount of terms to the point where the terms go on forever, Sn also approaches infinity. Another way to say this is as n gets bigger, Sn also gets bigger and bigger too. We can see this if we plug in some values for Sn. We can see that for S8, 9, 10, 11, 12, 13, and so on and so on, it keeps getting bigger and bigger continuously. It's diverging. It keeps getting bigger and bigger and bigger. So this second series down here, as r is less than 1, this series is convergent. So what this means is as n approaches infinity, so that means as we add more and more and more terms, Sn does not approach infinity. Sn approaches a set value that we'll just call k. We can see this if we plug in some values for Sn. We can see that Sn is getting bigger still, but it's slowing down as n increases to S5, S6, S7, S8, etc. And we can see that it's actually converging to a value. In this case, it's converging to a value, as you can see, of 2. So k in this instance is equal to 2. So diverging means it's getting bigger and bigger and bigger and won't ever stop. It will just go to infinity. And converging means it's converging to a value and will not keep getting bigger and bigger and bigger and go to infinity. Now, just to note, R for a converging series has to be less than 1, but it can also be more than -1 as well. Series like this converge as well, and they'll be the exact same thing, they'll just alternate as they converge. We talked about alternating series at the start. This is the same for a divergent series as well. It can be less than -1 as well as bigger than 1, as this would be diverging as well, but it will just be alternating as it does so. So a better way to write this is a series is diverging if the modulus of r is bigger than 1, or another way you can say this is if r is bigger than 1 or if r is less than -1. So it'll still be divergent, but it'll be alternating as it does so. And for a convergent series, the modulus of r must be less than 1. Or another way you could say this is if r is more than -1, but less than 1, like this. So in general, a series is divergent if the modulus of r is bigger than 1, and a series is convergent if the modulus of r is less than 1. So for a convergent series, there is something called a sum to infinity, and this is given the symbol s and then infinity like this, as it's Sn where n is equal to infinity. And this means that it is all the terms in the series added together, so the entire series, and this is what the series converges to. So S infinity is equal to a over 1 minus r, where a and r mean the same thing as before. A is the first term and r is the common ratio, and this is given to you in the formula booklet. So for this series up here, we know that a is equal to 1, as that's the first term, and r is equal to a half. So therefore S infinity is going to be equal to 1a over 1 minus r, so it's going to be 1 minus a half, and this is going to be equal to 2. So the sum to infinity for this series is 2. And this is of course what we expect, because we already saw that as n approaches infinity for this series, it starts to get closer and closer to 2, it converges to 2. So this is the sum to infinity formula, but this only works when the modulus of r is less than 1, because it needs to be a convergent series. If the modulus of r is bigger than 1, it's a divergent series and goes to infinity rather than a set value such as 2. So here's an example question. I've given you the sum to infinity formula because it's in the formula booklet, so you'll have access to it in the exam. And we're given this series here, and we need to find the sum to infinity, this geometric series. So all we just need to do is find a and r and sub them in. So a is equal to the first term, which is 320, and then r is going to be equal to, so the common ratio, so we can just do this by doing 80 divided by 320, which is a quarter. You can also confirm it by just doing another set of values. For example, you could do 20 and 80, so 20 divided by 80 is also a quarter, like this. So r is equal to a quarter, so therefore S infinity is equal to a 320 under or over, sorry, 1 minus a quarter, which if you put into your calculator is equal to 1280 over 3. So the sum to infinity, the value that the series will converge to is 1280 over 3. Just to remind you again that the modulus of r has to be less than 1. So this is a valid answer because r is a quarter and is less than 1. So this does work and does give out a sum to infinity. So here's another question on sum to infinity. I've given you the formula again because again it's given in the formula booklet. So we're told a geometric series has a first term 12k and a common ratio k, and we're told the sum to infinity is 6 and we need to find the value of k. So what we need to do is we need to sub these values into here. So the sum of infinity is 6 and this is equal to a, which is 12k, over 1 minus r, which is k, like this. We have a 12 here and have a 6 here, so therefore we can divide both sides by 6 to get 1 is equal to 2k over 1 minus k. I'm going to times everything by 1 minus k to get rid of this denominator here and put it onto this side here. So this is going to be equal to 1 minus k is equal to 2k. Move the k onto the this k onto the other side to get 1 is equal to 3k, and therefore it's going to be k is equal to 1 over 3. And then that's the final answer. K is equal to 1 over 3, so therefore the common ratio is therefore going to be 1 over 3, and the first term is going to be 4. So here's a couple of questions on geometric sequences. I've given you the formulas for Sn and S infinity for a geometric sequence, as they'll be given to you in the formula booklet, so you have access to them in the exam. So pause the video, have a go, and I'll go through the answers in about 5 seconds. So for question 1 part A, we need to find the common ratio of this series here. So we don't know what the first term is, but we know that the second term is 192, and we know that the third term is 144. And we need to find the common ratio, so we basically need to find what this is times by here to go from this to this, which is very easy. So therefore it will just be 144 divided by 192, and if you put this into a calculator, this is equal to 3 over 4. So r, the common ratio for this series, is 3 over 4. And then for part B, we need to find the first term of the series. Now, you could do this by using the formula for un and then plugging in values, etc. for something like the second term or the third term. That's a perfectly valid way to do it. But another way that you could just do it is obviously to get from the first term to the second term, you times by 3 over 4. So that therefore to get from the second term back to the first term, you just divide by 3 over 4. So the easiest way to do this is just to do 192 divided by 3 over 4, which if you put into a calculator is equal to 256. So the first term, a, is equal to 256. And then for part C, we need to find the sum to infinity, and therefore we can use this formula here. We can do this because the modulus of r is less than 1, it's 3 over 4, so therefore it's a convergent series, so therefore it will have a sum to infinity. So therefore the sum to infinity is going to be, so this formula here is going to be a, which is 256, which we figured out before, over 1 minus r, which is 3 over 4. Which, if you put this into a calculator, is equal to 1024. So the sum to infinity is 1024. So for part D, we need to find the smallest value of n for which the sum of the first n terms is bigger than 1,000. So as we're trying to find the sum of the first n terms, therefore we're going to use Sn here because it's the sum of the first n terms, where a is 256 and r is still 3 over 4 because it's the same sequence we're working with before. And n is going to be, so we need to find the smallest value of n for which Sn is bigger than 1,000. So therefore n is just going to be equal to n. And then what we can do is rearrange by making an inequality. So when this is bigger than 1,000, when the sum of the first n terms is bigger than 1,000, n is here, and then rearrange in order to find the smallest value of n and make n the subject of the inequality. So what we're going to do is we're going to sub the values into this here. So it's going to be a, so it's going to be 256 of 1 minus r, so it's 3 over 4, and then to the power of n. Remember, when it's fractions, put these brackets around the common ratio here, and it's to the power of n, and we'll rearrange in order to find this, over 1 minus r, so 1 minus 3 over 4, and when this is bigger than 1,000, when it's the sum of the first n terms is bigger than 1,000. And then we're going to rearrange in order to find n. So firstly, let's simplify this to 256 of 1 minus 3 over 4 to the power of n, and this is over 1 minus 3 over 4, which is a quarter, and when this is bigger than 1,000, and then we times both sides by a quarter to get rid of this denominator down here, so therefore it's going to be 256 of 1 minus 3 over 4 to the power of n, and this is going to be bigger than 1,000 times a quarter is equal to 250, and then we're going to divide both sides by 256 to get rid of this over here, so it's going to be 1 minus 3 over 4 to the power of n is bigger than, and 250 divided by 256 is 125 over 128, and then put this 1 onto the other side to do minus 3 over 4 to the power of n is bigger, and then it's going to be minus 3 over 128, because that's what this minus 1 is. And then we're going to multiply both sides by minus 1 to get rid of these minus signs here. There's going to be 3 over 4 to the power of n, but remember, when you multiply an inequality, both sides of an inequality, by a negative number, it flips the sign of this inequality. So this is going to be 3 over 4 to the power of n is less than 3 over 128, and then what we're going to do is we're going to take logs, because we have this power here, and we're going to take log base 10 of both sides, the standard log, so it's going to be log of 3 over 4 to the power of n is less than log of 3 over 128. You might be tempted to say that we could take log base of 3 over 4 of both sides, so we could say log base 3 over 4 of 3 over 4 to the power of n like this, which would of course just simplify to n, and when this is less than log of base 3 over 4 of 3 over 128, because then we've just simplified this straight away to n. The only problem with this is when this base is smaller than 1, you don't need to know this, but this would actually flip this inequality sign here, and to avoid, because this is quite complicated, and to avoid knowing about this, whenever you have an inequality, I would always do log of base 10 like this. Remember, we don't write the 10, and it just becomes a lot simpler, and the inequality sign stays like this. So I would just do it like this. So it's going to be log of 3 over 4 to the power of n is less than log of 3 over 128, and this is a power, so this can come down here as a coefficient. Recall the laws of log, so this is going to be n log of 3 over 4 is less than log of 3 over 128, and then we can divide both sides by log of 3 over 4 to get rid of this over here. Now, if you put it into your calculator, you will see that log of 3 over 4 is less than 0, so it's negative. So therefore, if we divide by log of 3 over 4, we need to flip this inequality sign here. The golden rule is that if this number is less than 1, the logarithm is always going to be negative, and if it's more than 1, it's going to be positive. So therefore, this is going to be negative, so if we divide both sides by log of 3 over 4, it's going to flip the inequality this way again. So, and now it's going to be log of 3 over 128 over log of 3 over 4 like this. So therefore n is bigger than, and if you put this into your calculator, this is n is bigger than 13.05. So we've solved the inequality here, we've solved this inequality, so now we need to find the smallest value of n. So n cannot be 13.05 because n has to be an integer, because we're talking about the sum of the first n terms. So therefore we need to find the first whole number that n could be, and the first whole number that n can be when n is bigger than 13.05 is n is equal to 14. N is equal to 14. The smallest value for which the sum of the first n terms of the series exceeds 1,000 is 14. It's 14 terms. So for question 2 part A, we need to show that k squared minus 7k minus 60 is equal to 0. And the original instance is quite difficult because it doesn't give us any direction to go, and it doesn't tell us what we need to figure out. So we just need to prove from this that this equation is true. So how do we do this? Well, the key to this is realizing that we have two equations that we can make that are equal to the common ratio r, because we have three terms. So to get from this to this, it's times r, and to get from this to this, it's times r. So therefore r is equal to, so as it's times r here, it's going to be k, the second term, divided by the first term, k plus 4. But r is also going to be this part here. So r is also going to be equal to the third term, 2k minus 15, divided by the second term, which is k. And therefore we can equal these to each other because they're both equal to r. So it's k over k plus 4 is equal to 2k minus 15 over k, and then what we can do is you can rearrange this in order to get an equation in this form. So first of all, let's times both sides by k to get rid of this denominator here, so it's going to be k squared over k plus 4 is equal to 2k minus 15, and then do the exact same for this side, multiply both sides by k plus 4 to get rid of both the denominator on this side and move it onto this side. So it's going to be k squared is equal to 2k minus 15 k plus 4. Expand the brackets to get k squared is equal to, and then expand the brackets to get 2k squared minus 15k plus 8k minus 60, and then we can simplify this to k squared is equal to 2k squared minus 7k minus 60, and then move the k squared onto the other side to get k squared, because the 2 is minus like this, k squared minus 7k minus 60, and this is equal to 0, which is what's required. K squared minus 7k minus 60 is equal to 0. So we use the fact that we have 3 terms and it goes up by times r each time, and we've made these 2 equations to rearrange into this form. And then for part B, we need to show that k is equal to 12, and this is really easy because this is just solving this quadratic equation here. So we can do it by factorising, by using the calculator, the quadratic formula. I'm just going to solve it by factorisation, so it's going to be k, and then k like this, and this is equal to 0. And if you figure it out, it's going to be that this is going to be minus 12, and this is going to be plus 5. This will give this minus 60 at the end when you multiply them, and when you add them, it will give this minus 7k in the middle like this. Okay, so therefore k is going to be equal to 12 and minus 5. So these are the 2 possible solutions. However, it only says that k can be equal to 12 because it says in the question k is a positive constant. So therefore k cannot be equal to minus 5. So therefore k is just equal to 12. And then for part C, we need to find the common ratio of the series, and this is really easy because we can use one of the equations that we made at the start for R and just sub in this value of k that we've got. So I'm just going to use this one here. So R is equal to k, which is 12, which you figured out before, over 12 plus 4, which is equal to 12 over 16, which is equal to 3 over 4. So R is equal to 3 over 4, the common ratio. And then for part D, we need to find the sum of infinity of this series, so therefore we're just going to use this equation here for the sum of infinity. We can use this because r is less than, or the modulus of r is less than 1, so therefore it's a convergent series. So we need to sub in r and a. So r we already know, but we don't know a yet. However, we are told that the first 3 terms of the geometric series are this. So therefore the first term is this here, k plus 4, and we know k is equal to 12, so therefore a is going to be equal to k plus 4, so it's going to be equal to 12 plus 4, so a is equal to 16. And now we can use the formula s infinity is equal to a, which is 16, over 1 minus r, which is 3 over 4. And if you put this into a calculator, this is equal to 64. So the sum to infinity is equal to 64.